We started talking about the definition of thermodynamics actually in the very first video for this chapter. And I mentioned that he would actually give you the definition for thermodynamics a little bit later on. And today is the day when he actually does that. So I have the definition back up here again, where thermodynamics study of the relationships and the conversions between different forms of energy. And today he also gives you two of the laws of thermodynamics. The first law of thermodynamics says that energy can't be created or destroyed, that it can only change form. Now this is slightly different from the law of conservation of mass that we saw early on, because technically the law of conservation of mass isn't exactly true. It is possible that you can convert mass into energy, so technically it is this law that is true. Now on the scales that we're going to be dealing with in high school level chemistry and physics, the law of conservation of mass certainly is going to be upheld. It's when you get into the like Einstein's theory of relativity and you get into some really advanced concepts that you will see that mass can be converted into energy. So for our purposes, you will still see the law of mass conservation is going to be obeyed as far as this course is concerned. But this is actually a better way to state it because mass can be converted. So we've actually already seen this principle take place when we talked about enthalpy, because we saw that potential energy was converted to kinetic energy, or kinetic energy was absorbed and then that was turned into potential energy in a reaction. Okay, so we've seen this already with enthalpy. The second state function that we are going to introduce in this section is called entropy, and it is abbreviated with a capital S. The author of your textbook defines entropy as the energy unavailable to do work. Now if you think about that, let me give you an example to see if I can make that a little bit more clear. Perhaps you are out running some sort of a sprint, maybe with your buddies outside, and you pour everything you've got into sprinting as hard and as fast as you can into winning this race. And so you may even say, I gave it everything I had. Well, in reality, you didn't, because you still had to have some of that energy to breathe. Your heart had to have the energy available to continue beating. If you had lunch earlier in the day, maybe you were still digesting some of your food. And so all of those things had to continue to take place within your body while you were running. And so all of your available energy you could not pour into running, because part of that energy still had to be used to maintain your other bodily functions. And so that's one way to think about the idea of energy that isn't available to do work. You weren't able to harness every bit of energy you had for the race because you had to keep your body functioning, even if you weren't conscious of it. Okay? Now, it's actually a little bit easier for our purposes to think of entropy as a measure of disorder that exists in a system. And you may actually want to jot that down. I don't know if you generally take notes during my video lectures or not, but this would be a good thing to jot down, that entropy, an alternate definition for it, is the measure of disorder that exists in a system. And so let me see if I can give you some examples as to, again, what that kind of looks like. This all plays into the second law of thermodynamics, which says that the entropy of the universe, or the amount of disorder that exists in the universe, can never go down. It either has to stay the same or it has to increase. Now you may be thinking about that and going, hang on a second, that doesn't seem to make any sense. My mom makes me go clean my room, and when I clean my room, obviously I'm decreasing the amount of disorder that's in there. Well, it may appear that way to our eyes, but let's face it, when you go in to clean your room, what you are doing is you may be moving objects around and putting them in a position that looks a little bit more neat, but you are disturbing the dust that's in there and making it rise up and move around. So that is going to increase the disorder of the room as a whole. The other thing that happens is, I know when I clean the house, I tend to get hot just because I'm working hard. And so when I give off body heat, that's going to heat up the surroundings around me, which means that the particles in the air are going to be moving faster. So it is going to increase the disorder of the air. So in reality, while your room may look better, you actually can't decrease the total amount of entropy or the total amount of disorder that's in your room. So kind of just to keep in mind that just because we think maybe we're decreasing the amount of disorder, that it's only at the level that our eyes can see, we really can't decrease disorder in the universe as a whole. It either has to stay the same or it has to increase. So entropy is going to increase in about 3 specific circumstances that, let me see if I can explain those to you. So if I go from a solid to a liquid to a gas, entropy is going to increase. So think about the particles of a solid. We talked about this in an earlier chapter. In a solid, all of your particles or atoms are all lined up in a box type situation, and all they do is they sit there and they vibrate. When you go from a solid to a liquid, the particles or the atoms, the molecules are, instead of just staying in one place and vibrating, they start moving around a whole lot more. They start bouncing off the sides of the container. You saw this when you put food coloring in a liquid, and you saw that the warmer the liquid was, the faster the particles were moving. And so as you go from a solid to a liquid, there's more disorder, there's more motion happening. And certainly when you go to a gas, now you've got your particles even further spread out. The further spread out they are, the more disorder there's going to be in the system. The faster the particles are moving, the faster they're bouncing around. And so again, from solid to liquid, from liquid to gas, as you go this direction in your phase change, your entropy is going to go up. Similarly, as temperature goes up, entropy is going to increase as well. So again, think about the experiment that you did where you put food coloring in warm water and you put it in cold water. You saw that the particles were moving a lot more in the warm water because the food coloring got mixed up a lot more quickly. So there's more disorder in a system when the particles are moving around a whole lot more. It's just a whole lot more disorganized. So as temperature goes up, entropy is going to go up. And additionally, as the amount of matter in a system increases, your entropy is going to increase as well. You can kind of almost picture this situation. I think of my husband's grandmother, and she was one of the sweetest ladies that you would ever have wanted to meet, but she tended to be a hoarder. She tended to just keep all kinds of stuff in her house. She never threw anything away. And even though everything was stacked up, it just seemed like she had so much stuff in her house that the whole house just looked like a wreck. I mean, despite the fact that it may have been stacked neatly, just the volume of stuff made her house just look like a disaster. So as the more stuff you have, the more matter you have, the more entropy increases in a system. Okay, so keep in mind, again, if you have not been taking notes, you may also want to jot these 3 things down, that these things will cause entropy in a system to increase as you go from solid to liquid to gas, as you increase temperature, and as you increase the amount of matter in a system. We are going to look at a couple, actually 4 specific reactions and try to determine from looking at them what is happening to the entropy of this particular system. And so if entropy increases, that means if it goes up, that means your delta S is going to be positive if entropy is increasing. So I want to make sure we get the sign on that straight. These 4 equations that I have on the board are also on the sample problems for the videos that I gave you in a separate document. So if you want to look at those as we're talking and make notes on that, it's the very same equations that I have here. So if we look at this first equation here, I've got C2H4O2 reacting with, this is sodium bicarbonate, which is actually baking soda. And it gives me sodium acetate and water and carbon dioxide gas. So if I think about the fact that going from solid to liquid to gas increases my entropy, if I look at the left-hand side of the equation, I have something that's aqueous. So I can think of that, that's basically liquid form. It's aqueous, so it's going to be in liquid water. And I have a solid. On the opposite side of the equation, I have an aqueous and I have a liquid, and now I have a gas as well. Gases are always more disordered than aqueous solutions or liquids or solids. And so just the fact that there is a gas on this side of the equation is going to indicate that the delta S for this solution is going to be positive. It is going to increase once this reaction proceeds because of this gas right here. Okay, let's look at the next equation. The next equation, I have some ammonium nitrate with a barium hydroxide molecule, and you'll see this water. This is similar to what we saw if you were able to do the experiment with the copper compound that had water built into its structure and then you drove that off. It's called a hydrated compound. You probably remember doing that in one of the earlier chapters. And so when I put these two solids together, what happens is that the water comes off in liquid form, and then I end up with two aqueous solutions on the other side. So here again, I have solids on the left, I have aqueous solutions and a liquid on the right. And so just by virtue of the phases of the things in this reaction, again, my delta S is going to be positive. Entropy is going to increase, okay? So far what we're seeing here, the entropy is going to either stay the same or increase. Let's look at this one down here. Here I've got hydrochloric acid in a gaseous form with ammonium hydroxide in a gaseous form. And when those react together, I end up with solid ammonium chloride and liquid water. So this is the opposite of what I was seeing in the first two reactions, where I've started off with gases, but now I'm ending up with solids and liquids. So here on this particular equation, my delta S is going to be negative. And you're probably thinking, hang on just a second, because you just told me entropy of the universe can never go down, okay? That part is true, but what you have to remember is this little prepositional phrase in here. The entropy of the universe can't go down. When I look at an equation, I'm only looking at the entropy of a specific system. And so this system is going to react with other things around it. And so if the entropy of this system is going to decrease, then likely the surroundings, their entropy was going to increase. Similar to when you were cleaning your room, you may be decreasing the entropy of all the stuff in your room of that particular system, but the surrounding air had its entropy increase because you were working up a sweat. Okay, same type of thing that happens here. So when we do this, we are defining a particular system. We're not looking at the universe as a whole. Okay. So again, because we went from gases to solids and liquids, entropy of the system went down, and so delta S was negative. Then finally, if I look at this last equation, sulfur dioxide plus some fluorine gas is going to yield a sulfur hexafluoride gas and some oxygen gas. Well, here everything is gas, so how do I determine on this one what's happening to the entropy? Well, this is where the amount of matter in the system comes in. If I look here, I have 1 mole of sulfur dioxide and 3 moles of fluorine gas, which is a total of 4 moles on the left. On the right, I have 1 mole of sulfur hexafluoride and 1 mole of oxygen, so that's a total of 2 moles on the right. So I've gone from 4 moles on the left to 2 moles on the right. And so since I've decreased the amount of matter, that also means, that the entropy of my system is going to go down as well, since I've decreased the amount of matter there, okay? So you're going to be just looking at equations and determining from there what's going to be happening to the entropy of the system.